Alright, so today we're going to be doing 4.1a, which is extreme values of functions. So this will be the first of chapter 4. Okay, we're done with chapter 3. Chapter 3 was all about like finding different types of derivatives. Every type of function now you basically know how to differentiate, except for like extreme outliers that are more advanced. But you basically know all the basic derivatives now. So now chapter 4 is all about application of derivatives, how we can use derivatives to analyze other situations, figure things out. Alright, so first thing we're going to look at is extreme values. So an extreme value is basically a maximum or minimum. Extreme value is more broad because it encompasses absolute and local maximums and minimums. So, for example, as you can see, this is a local maximum, and this is an absolute maximum. Absolute is the highest value possible, and then local is going to be where we change from increase, decrease, or increase, decrease will be an absolute or a local maximum, depending on how high it is, right? So do you see why this one is absolute and this one is local? This one's higher, right? So a lot of maximums and minimums occur where the derivative is what? If it's completely flat, the derivative is 0, because the slope is 0, right? Derivative is slope. So that's often where we can find local or absolute mins and maxes. But additionally, we have to look out for different things that may be addressed as minimums or maximums. So what do you notice this one? Could you differentiate at this point here? Can you find the derivative at that point?
Yeah.
You can find the derivative at a cusp or a corner? No. So that's why this is so important to address. So the easy ones to find are the ones that have the derivative of 0, because you take the derivative set equal to 0. Those are the easy ones to find. The harder ones are ones that are cusps, corners, vertical tangents, discontinuities, because those are not as straightforward, okay? Because we can't just take the derivative set equal to 0 because the derivative simply doesn't exist here. It's not differentiable, okay? All right. So these are some examples of critical points. So you're going to learn more about critical points, which ones are useful, what critical points do what, all that stuff in future lessons. But for today, you're only going to really be talking about how to find the critical points. Okay, so there are reasons for why we find them, there are applications for them, all that stuff, but today is specifically focused on just finding them. So there are extreme values that occur at critical points, also at endpoints, and not every critical point signals the presence of an extreme value. So that's really important. Not every critical point we find today will be that useful. Okay, sometimes you find extra information, and that's okay. So this one here, does everybody see why this is a critical point? Because it is a maximum and it has a derivative of 0, so we would call this a critical point. And that would be a quadratic function, right? Quadratic functions always have one critical point at their max or their min, also known as the vertex. What type of function family does B belong to? Cubic, good. So cubic functions will have a critical point right here because the derivative is 0. There we have a horizontal tangent line. However, this critical point does not indicate a max or a min, right? Because we're still strictly increasing. We just changed the rate at which we increase. Does everybody see that? This one here is a critical point because it signifies a cusp or a corner. Okay? Cusp and corners are known as critical points, but they are non-differentiable. So they occur where their derivative does not exist. And then does anyone remember what type of vertical tangent? Good. So vertical tangents are also critical points because they are points where the derivative does not exist. So we're always looking for where the derivative is 0 and where the derivative does not exist. And there's a few different ways the derivative cannot exist also that we don't talk about as much, which is like if you have a square root function, okay, that's values which we cannot plug in for x because they don't exist. That would be, we can't differentiate where the function doesn't exist. So keep that in mind as well. All right. So these are the steps to finding critical points. I'm not sure why this happened, but just keep in mind there is a step 4. I just accidentally shuffled the photos up too high and it went between the 3 and the 4, but just be aware there is a number 4 there. So you guys should be super, super familiar with these 3 types, removable, infinite, and jump. Everybody remember those 3? Yeah. So removable is where you have a hole. That's where you have something that cancels out of the numerator denominator but is undefined. Infinite is a vertical asymptote. That's where you have a graph of x over x minus 3. Okay, you have a value at 3 that cannot be canceled. It's in the denominator. That's where vertical asymptotes come from. And then jump discontinuity really only occurs in like a piecewise function, where you have different pieces of the function and they don't necessarily all line up this way. So then we have the other types where we have critical points, which are sharp corners and cusps, and then vertical tangents. So something that you're going to need to know that's kind of new information to you guys is, anytime you have x to an even over odd power, you know you're going to have a sharp corner or cusp. So you should be able to remember that, recognize that if I give you something like that, you should be able to know it has one of those. Okay, so if it's like x to the 2/3, you know it's going to have a sharp corner or cusp. Vertical tangents occur where we have odd over odd power. Okay, so that's like you know, like 1/3, anything like that is going to have a vertical tangent. So you should be able to now identify that with me just telling you what the power on the x is, if you have one of those things. And then here's the vocabulary. We call it a critical point when you have the whole point. The critical value is the y coordinate, and then the critical point occurs where the x is. So just be aware of the different vocabulary. All right, so example 1, we're going to go through the steps to find the critical points. So the first critical points you always want to find are where the derivative is 0. So you can simply take the derivative, which is going to be what? What's going to be the derivative here?
Squared
Plus
14x plus 15.
Good. Okay. And then we can set this equal to 0, right? So when I set this equal to 0, my goal is now going to be to solve for x. Okay, we don't need that part anymore. So how would I go about solving this for x?
You'd move the 15.
That doesn't work for when you have an x squared, an x, and a constant.
We have to factor.
You have to factor. And in this case, because it has an a, you have to do the AC method. You guys remember this? So the thing about math is nothing ever goes away. So you always have to know how to do everything beneath you. That's the good and the bad about it, right? So factors of 45 that will add up to 14 will be 9 and 5. Everybody good with how I got that?
Yeah.
Now, because we did the AC method, we have to divide by 3, which gives me x plus 3. And then you could bring this back over in front if you want, but I'm not going to because we're just going to solve it, right? So now I'm going to set each of these equal to 0. So when I set this equal to 0, what's this going to give me, the first one?
3.
Negative 3.
And negative 5/3, good. So then from here, our goal is to plug these values back into the original function to find the entire critical point. So right now we only know where the critical point occurs. We don't know what the critical point is because we only have one of the coordinates. Everybody an understanding of that? Okay. So in order to do that, we need to plug it back into the original equation. Not the derivative, but the original. If you plug it back into the derivative, you're just going to get 0 because that's how you got it to begin with. So that's redundant. So we plug it in. I'm a little bit lagging as always because, you know, technology. So this gives me negative 27 plus 63 minus 45, which is negative 9. Now the other one, you all have the skills to plug this in, right? Negative 5/3, it's just kind of gross. So we're not going to actually plug it in because we're just going to look at the Desmos graph because I don't want to waste time on plugging stuff in here because you guys know how to do that. So as you can see here, I've graphed this on Desmos, the actual equation. And do you see the negative 3, negative 9 that we just found the critical point? Do you see why that's a critical point? It's where the derivative is 0. Okay. Additionally, we also have this as a critical point where the derivative is 0. Now, if you do negative 5 divided by 3, that's with that decimal, negative 1.6 repeating. So this right here is the corresponding y value. So you guys can just copy that down from this. It's going to be negative 10.185. So everyone understanding about that. Now, if you look at the rest of this graph, you're going to see there's no other critical points because this is a polynomial. Polynomials are going to be differentiable and continuous everywhere. So with polynomials, you don't have to worry about all of the other stuff. You don't have to worry about the cusps, the discontinuity, any of that stuff, because those functions just simply don't have any of those things. So with this one, that's basically all we have to worry about. Now normally, you would then find all the x values for which the derivative is undefined, but like I said, the derivative is defined everywhere on this function. So that's it for this one. Now for the next one, we have this function. Step 1 is going to be to take the derivative. Yes?
Would that be considered like f of x equals x even over odd?
Even though what?
Like even over odd?
You're right. Yeah, that's going to be part of it when we get to the point of where the derivative is undefined, number 3.
Okay.
Yep, you're right, though. Yes. So that's a good point. Even though we see this as even over odd, we still have to find where the derivative is 0. That's the first step 1. Then we have to address it and see if the derivative is undefined anyway. So let's go ahead and do that. We're going to take the derivative using the chain rule. And then, of course, times the derivative of the inside is just 1, because derivative of x minus 1 is 1. So is everybody good with that? Yeah. Now remember, our goal is to set this equal to 0 and solve for x. So you have a few different options to doing this. Right off the bat, I try to get rid of the constants. If I'm setting something equal to 0, I can just divide by this, and now it's gone, right? So now I just have this, which I can rewrite as this. So is everybody in understanding of how that's the case? Third root. Okay, bring it down to the denominator, convert it from exponential fraction to a root. Now let's think about this for a second, and this will help you through all of these problems. When a fraction is equal to 0, that means that the numerator is 0, right? It doesn't matter what the denominator is, except for if it was 0 over 0, which is undefined. But if you have 0 over 5, 0 over a million, those are all 0. So we don't really care about what this denominator is to make this 0. We need to make the numerator 0. Is there ever a case where we can make this numerator become 0? Well, I see where you're going with it, but is there a variable that we can plug in up here that's going to make this? No. See how there's no variable? So that is stuck at 1. Forever. So is it possible for this derivative to ever equal 0? No. No. So this is no critical points found. Wow. Just from the derivative part. We still might have critical points found in the other ways, but right now the derivative, we don't have any values where the derivative is 0. So what that basically means is there's no spots on this graph where the slope is 0. Okay? So maybe this is a little too confusing for you guys. If you don't want to write, there are technically no critical points found from here, but the derivative is never 0. Maybe that's more clear, because technically that's true, but I just want to make sure you understand there could be other critical points from the other methods. So does everybody understand why the derivative here is never 0? Okay. Now, with that being said, that doesn't mean we don't have other critical points. So if we look at this, notice what Jacob was saying earlier. What is the power on that? Even over odd. What does the notes tell us about this?
It's a cusp.
It's a cusp or corner. We don't know which. We kind of treat them pretty similarly. They act very similar. So we know we have a cusp or a corner on this graph. So here's how you can figure out where that cusp or corner is without using any graphing technology. You're going to take whatever is to that power, the even odd power, okay? And you're going to set that equal to 0. Whatever is to the power, you're going to set that equal to 0, and then you're going to solve for x. So x is equal to what?
1.
So we know that we have a critical point at, specifically a cusp or corner at 1 comma. To find the y, you would plug that in. That's 0 to the 2/3, which is 0. That makes sense to everybody. Now, the good thing about all this is you can confirm this using graphing software. So do you see this particular graph? If we zoom in a little bit, do you see how we have a cusp or corner at 1, 0? Mm-hmm. Okay. So if I were to give you a graph of this, you should also be able to visually identify it as well. Not just using the algebra, but also graphically. Any questions about that? Yes.
Will there be a way that we can tell, like, off the bat that it won't work? Like, there won't be a derivative at 0 or derivative of 0? So
yes.
Just straight to the even over odd?
I can tell by looking at it just from the fact that I have a lot of the more knowledge you have about functions, the more you know what functions look like. But there's really no like easy way to tell. It's just like experience, I guess. So that's why, yeah, that's why I teach you like the methods, because like until you're comfortable enough. I know this graph we call it like the little bird, like it looks like the drawing bird. Anything that's x to some even over odd power looks like that. And I know that it doesn't have any other critical points. So yes, I know that, but like there's no way to know it. It's more like sight recognition. Yeah, unfortunately. All right, so the next one. So this one here, and you're gonna notice with a lot of chapter 4, the more you like have a good knowledge base of math and functions, the easier it's gonna be for you. So this one here, first thing we're gonna do is we're gonna have to take the derivative. So you might be thinking product rule. That could be a correct way to do it. But if you don't want to do product rule, you can also just distribute here, right? And I'm able to do that because there's no power on that binomial. So I'm just gonna rewrite it before I even take the derivative, just to make life easier, so I don't have to use the product rule. But if you did use the product rule, that would also be acceptable. Now, when you multiply two common bases with different exponents, you have to add the exponents. So this is technically 5 over 5 on the x, right? 1. So what would be 3/5 plus 5/5?
8/5.
8/5. So that's like just a shortcut. Now keep in mind we haven't taken the derivative yet. We still have to do that. So y prime is equal to, this is going to come out front times the 4, so that's going to be 12/5, x to the negative 2/5, so just subtracting 1.
Wait, why is it 12/5?
Because the fraction comes out front, so 4 times 3/5.
I see, okay.
Yeah, it's like a lot of fraction work in
Yeah, I
here.
thought you were using the 8/5.
No, I get what you're saying.
That's not 12.
Yeah. And then 8/5 minus 1 would be 8/5 minus 5/5, which is 3/5. So it's just a bunch of fraction stuff. And then remember, your goal is to set this equal to 0, right? So there's several different ways to actually solve this, whatever you're comfortable with. However, what level of comfort you have with algebra is going to come down a lot to what you do here. So if I want to get rid of a fraction in anything, I can multiply both sides. So you see how the denominator on both of these is the same? I can multiply both sides by 5, right? Which is going to cancel out my fractions over here. And then this leaves me with 12 over. Remember, negative exponents I can bring to the denominator make positive. This one's not negative, so it's going to stay up top. And that's all equal to 0, right? I'm going to keep this over 1, so you can see why in a second. Now, what I'm going to do to solve this, there's multiple ways to go about this, but what just strikes my memory the most is when I have two fractions subtracted from each other, I like to get them on opposite sides of the equal sign, because now I can do what? Why is this beneficial in solving? What can I do now?
You can get rid of your exponents?
Yeah, essentially by, yeah. So what you're going to notice is this becomes 8x to the, remember you're adding the exponents when you multiply. It's just x equals 12. So x equals, which is 3 over 2. So 3 over 2 or 1.5, right? So that's one of our critical points. So the reason I knew there would be one here is because it wasn't just a plain x to the power of 3 over 5, an odd over an odd. It's times another function. So that, you know, is typically going to have a critical point. So that gives you like some insight about what's going to happen. Now, we know that additionally we have to figure out, of course you got to plug this back in. I'm going to show you an easier way to do that by just looking at Desmos, but we'll plug that back in eventually. But it says find all the values for which the derivative is undefined. Well, looking at this, do we have an odd over odd or even over even anywhere, or even over odd anywhere? This piece right here, right? So what that means is I would set what is to that power equal to 0. So if I set what is to that power equal, it's just x equals 0.
So you just have another critical point at 0.
Another critical point at 0. And then of course, algebraically, you guys all know, you can plug an x back into a function to get a y. We don't have to go over that part. But we can look at the graph and determine where that's going to occur. So if you look at this graph here, do you see the vertical tangent at 0, 0 that we knew was going to come up because it was odd over odd? In addition, do you see where the slope is 0 at 1.5, which is the same as 3 over 2? So you guys can copy down the y coordinates right off here on Desmos. On the test, yes, you would have to plug it back in to find it. I probably wouldn't give you something super difficult. I might also give you questions where you look at a picture of a graph as well. Any questions about that? Yes?
Can you re-explain where you got the 0 from? I'm sorry.
Sure. So with this, do you understand why there's a vertical tangent somewhere in this? Because of the 3 over 5?
Yes.
Okay. So whatever x is to the power of that odd over odd, you're going to set that x equal to 0. So like, see here, we had x minus 1 I had to set equal to 0 to find it. This one is simply just a plain x. So when I set the inside, what is to the power equal to 0, it's just x equals 0. There's no solving required to find out where that occurs. So it's always kind of weird when there's nothing to actually solve for, but it just tells me where that would occur.
All right, thank you.
You're welcome. Any other questions about that? All right. So some important stuff before we finish here. When I hand out your homework, you only have to show work for 1 through 6. Okay, you're going to find the critical points just like we did on the notes. 7 through 10 are tricky. They're going to be like a lot of algebra stuff. So you guys can put it in Desmos and just look and find, look for vertical tangent. It's a good practice for the visuals, vertical tangents, cusp, holes, all that stuff. And look for where the derivative 0, of course, and you can visually find it. But then I want you to each pick one of those questions to show the math. Okay, you can pick any one that you want. I'll leave this up while you have the homework. And then also practice identifying the types of critical points. So for example, this critical point is where the slope is 0. What's this other one? Vertical tangent, right? This is a vertical tangent. And this one over here, the slope is 0. So practice identifying that because that will come up on the test. So it's good to practice now identifying those critical points. Your next test will be 1 week from tomorrow on February 7th, and it will cover these 3 sections. All right, I'll go